Hi, everybody. So this is Mrs. Braband, and what I'm going to do is I'm going to review or repeat, actually, Unit 1D, Day 3 on algebraic domains, simply because in yesterday's session, we lost a few minutes of Zoom, and today for fifth hour, we lost a few minutes with the crash. And some of you were able to obviously get back on and do the whole lesson, but I know some of you were not able to do that. So this is going to be a repeat of what you saw or didn't see. Again, finding algebraic domains. Your homework is going to be Math Excel. I will also, let me type in here too, I'm also going to be uploading a worksheet that you will upload your work with, again, due Sunday, okay? So keep that in mind. So we started with this and thought we've already done these before, like with decimals and stuff, and we just kind of asked ourselves, what connections do I see between the graph, the equation, and the actual answer that we're getting? And so what we're going to be doing today is focusing on this, getting this answer today. So I wanted you guys to notice some things, and some of you were really smart and you understood by very good observation skills that if you factor this problem here, -4 and -3 and 4 were your factors, and that magically was also where the starting and stopping points for the function were. So the graph you see is actually this function. That's not apparent we normally do, so that's why I wanted to just have you see this one. It sometimes comes up. So when writing the domain, you can see that from the left to -3 is the first part of the writing, and from the 4 to the right is the rest of the domain. The whole thing is what we would be getting. So that's what we're going to work on today, is how do you go from an equation to this domain. So we reminded ourselves that the x values are what we're trying to name. We'll be doing interval notation. And when we pick the right x values, it'll allow our function to actually exist. We'll be able to tell people where on the graph to look. We are functioning with algebra today, so you can always pull up decimals and look at your graph, the physical part of the graph, and try to go from there, but we're really going to be doing all the algebra that goes there. We reminded ourselves that parent functions usually have a negative infinity to positive infinity domain, typically, except for a few ones down here. So the ones in yellow, remember, are the ones, except hang on, the exponential one does work. Let's get rid of that. This works. The ones in yellow are the ones that have, what I sometimes call wonky domains. In other words, there's the stopping point, or there's a break, starting asymptote, breaks and openings, but this actually is okay. It's just a little weird. So again, if it's a normal one, we're going to use it. If it's not, we're going to show the breaks with algebra. Here we practiced interval notation from Algebra 2 because all our answers are going to be in interval notation. We'll be doing algebra and getting these in front of us, but we want to make sure we do the pre-calc version of that. So this one is, I'm going to start at 5, not include it, no equal bar. I'm going to go to the right. The next one is just answers between -4 and 9. So answers between -4 and 9. I look at the bars. They are included. So I say people, make sure that those are solid, not open. The next one is everything bigger than -7. So I start at -7 and I go to the right. But I don't include it because there's no equal bar. The last one is a little tricky. You just have to be careful when you're describing it. So it looks like it goes everywhere from the left of -2. Then there's a big jump, and then everything to the right of 5. So it's going to be a picture super similar to what we just did before, probably. So we're just going to write what we see on that one. So we're going to, again, go everything to the left until I get to -2, and I do like it because there's an equal bar. Then I'm going to keep going, but now I'm going to jump all the way over to 5, and I do like it because there's an equal bar. And then I'm going to keep going to the right. So we're going to be doing algebra steps to get some of these answers, and we just have to be consistent with our interval notation. This was just a quick check again to hey, do you remember what's going on from the past? And can we think about the graph of algebra, or the graph of the function that'll help with the domain? This is just a typical quadratic, even though there's a weird wonkiness in front of it. It's not a variable in the front. It's just a coefficient that's going to shrink my graph. So this is typical parent graph. So I know it's negative infinity to infinity. It's just, shrinking vertically. The second one is a radical. Some of you call that the swimmer's arm. So it starts at right 1 and then goes off to the right. So listen to what you just said. It starts at 1 and goes off to the right. Again, our goal today is naming what's allowable to use for x's. The right one, far right one, is trickier. We've never graphed that before. You can obviously put it in decimals to see what's going on graphically. I'll show you what it looks like. So you can see that everything works but that 5. So we've just got to kind of talk about that. So the x on top says, we've got to be bigger than, positive 0. But the bottom one, which is the big indicator, is saying you cannot have a 5. So if you look at this, look at what you're doing. You're doing negative numbers. Oh, merciful heavens. Hang on, Nellie. Back that baby up. I forgot to talk about the first part. Well, I talked about it. I didn't write it. This guy here in the numerator tells us I have to be bigger than or equal to 0. This guy in the denominator says I cannot be 5. So, look, I have to start at 0, go to the right, jump at 5, and go to the right. So let's be careful with that. I have to start at 0, go to the right, jump at the 5, and then keep going to the right. So again, we just got to be super careful with what makes this function kind of break up. So it's, different than the usual. And when I say the usual, I'm saying the typical parent graph that goes from negative infinity to infinity is what I'm calling usual, this kind of domain here. If it's not the negative infinity to infinity, there must be a break, and we got to find out why. So let's do a few. These are the rules that I just said. So if you want to take a quick look at those, come back to that, you can. Again, if there's a variable in the denominator, we are careful with our breaks. And if there's an even root anywhere, top or bottom, we need to make sure that what's underneath the root is positive. So that's why you're getting, denominator can't be equal to 0. Anything under a radical has to be positive. So those will cause the breaks and change what our typical is. I'll let you see the steps. You can come back to that and look at it, but it's kind of a repeat of what I just said. Typical domain, done if it's a usual parent. If it's not the usual, it has radicals or denominators, then there's going to be breaks. And so we have to be careful about how we're going to find those breaks by doing some algebra to work that out. Okay? And everything's going to be written in interval notation. You can come back to this if you want. Let's try a few. Okay, step 1, is it a parent? Number 1 is. It's a typical quadratic flipped upside down. It's not factored, so it's hard to see where the x-intercepts and stuff and the shifts are, but that's okay. We know it's quadratic. So I'm going to get a usual negative infinity to infinity right there. So I'm not going to overthink it. Oh, the last two, they look a little messier to me. So they've got a radical. That's a problem I'm going to have to remember about. There'll be a starting point there, like a shift. And then the bottom one has a denominator with a variable. So that's going to be another break. So let's do the second one. It's not factored. You can definitely factor and get the shift if you want, but you can also just say to yourself, I need to make sure that this guy is greater than or equal to 0 in order to work, and then just solve it. So move your 9 by addition, move your 4 by division. So you know now that in order for this to work, you're going to start at that shift of 9/4. So again, there's a shift and a shrink here. So we're not graphing it, we're just doing domains. So again, you're starting at 2 1/4, that's 9 divided by 4. You can leave it 9/4 if you want. And then you're going to the right because of the word greater. And then you're done. There's your domain. Let's do this last one. The bottom's a problem. It cannot ever be 0. So we have to stop and go, let's check. Let's make sure, tell people that this can never be 0. Let's be careful. We'll move that 4 by addition. that's going to say to us we can never have, now take the square root to both sides, we can never have either positive or negative 2. So we're basically saying use everything in the world that you want on the left of one number, use everything you want between the two numbers, and use everything you want on the right of the number, but don't hit negative 2 and don't hit positive 2. So let's just be careful with saying that. Everything to the left I can use until I get to negative 2. It's a comma, sorry. I can't use it, so don't bracket. But then I got to jump over that little gap. I'm going to keep going until I get to 2, and then I got to jump again over 2 because it can't work either. And I keep going to the right. Again, if you need to put it in decimals to see why that algebra works, you may do that. Let's try a few more, and then we'll call it. The rules are off to the right to remind you. But again, you're going to always ask, is it a typical parent? If so, get it in. If it's not, watch out for the breaks. Okay, so number 4. That's a cubed root, shifted right 7. So I know it looks something like this. That's typical to me. Let's just write it. No overthinking that one. Second one, it's a radical. Okay, it's an even radical. So that's this rule here. So I've got to take this guy here. This is the one we did earlier, isn't it? I got to make sure it's greater than or equal to 0. I have to see the factors to get that done so I can understand where the breaks are. Greater than or equal to, sorry. So again, if I solve the left one, it's going to be 4. If I solve the right one, it's going to be negative 3. If I'm writing it in domain, I go left to right. So this basically says to me, I'm going to go everywhere from the left until I get to 3. And then I'm going to go everywhere until 4 after. So there is a break in the middle. Don't forget that. So here we go. Coming from the left until I get to negative 3. Big break in the middle, and then from the 4 on. So again, I know you're not used to using that square under a radical where there will be a break. Remember the one we did earlier with the wings. That's kind of what's going on. So that's just another function to start looking for. 6. Let's see, it's not typical. It's a fraction. Okay, so if it's a fraction, I'm going to be looking here at that rule. So I don't have to worry about the top because there's no letters. So let's not worry about that. But I do have to worry about the denominator because there's a radical with a variable. So I have to say, not only can this not be, I mean, look, we got both of these babies going on actually. This cannot be equal to 0. But even more specific, what's underneath the radical, called the radicand, has to be positive. Now, normally I put a bar right there. But if it's in the denominator, it can't be equal to 0, so I don't want the bar. So we're kind of killing 2 birds with 1 stone by taking out that bar. So when the radical's in the denominator, don't use the bar. Okay, let's solve this one. If I square both sides, I'm going to get x plus 5 equals 0. Okay, not equal 0, sorry. And that's undoing the radical. Now let's undo the 5. So x cannot be negative 5. All right, we're going to be jumping over that. So keep that in mind. This guy, if we move it to the right, we're going to keep subtraction going. So x is greater than negative 5. Okay, so that and that together basically means I'm starting at negative 5 and going to the right because of the greater word. But the not equal sign means I can't use negative 5. I have to parenthesis that and not include it. So I'm going to start at 5 but not include it. Then I'm going to keep going to the right because of the word greater. And I am done. So that's the lesson. We've done all types there. Again, normal apparent graphs are negative infinity to infinity. Wonky situations like radicals and denominators with variables, that's when you have to stop and use these algebra rules to find your breaks. Hope that helped. Reach out if you have questions. That's it, people.